Hello everyone, very welcome to our platform once again, and that is Carrier Wave. So today we will be discussing about the mechanical properties of fluid. So we have already discussed in the demo section, that was the thermal properties. Now we are talking about the mechanical properties of the fluid only. This chapter is a little bit complicated in nature. There are several of the topic that are continuously confusing. So that means this lecture would be a demo session for the English medium batch. Okay, so the entire conversation would be in English. And if you are already enrolled in the batches, that means there is no need to watch this video, or else you can watch it and have a clear picture of how we are gonna cover it in the batches also. Okay, so let's start. First of all, the first topic is, as we talk about the fluids, the chapter is talking about the fluid. So what is fluid? Fluid means something that can flow. That means that must be having a property of fluidity. Fluidity means the flow property, something that can flow. And that two things can be the liquids and the gases. Even the gas can flow, even the liquid can flow. That means whenever we talk about the fluid, that means it contains the liquid as well as the gases itself. Okay. Now, once we continue with that, we find out there are several of the things that cannot be very much effective in the fluids. Like in mechanics, we were talking about the mass, we were talking about the forces. But in fluids, we find out that there is no such thing as a mass that we can calculate on the basis of a large volume reservoir. That means instead of talking about the mass, we talk about the density. Means as we discussed the masses there, the same analogous that acts here is the density. You won't be finding any of the formula that contains the mass in this chapter. Why? Because instead of mass, we use density in the fluids. The next thing is, instead of forces, like we talk about the forces, several of the forces in the mechanics, but here you won't be getting the term forces, you would be getting the term pressure. That means instead of mass and forces in the mechanics, here the analogous becomes the density and the pressure. Okay, of course we can convert and we can derive it along the way, but the thing is the density and the pressure becomes more handy when we talk about the fluids. Now let's talk about the density. So as we already starting, so that means we would be starting with the density and then the pressure. Then we will be coming to the continuity equation, Bernoulli equation, airlift, capillarity, adhesion, cohesion and all that. So first of all, let's start about the density. As we know that there are several of the materials, like there is a state of matter called solid, then called liquid, then called gas, right? As we see in the solid, there are the molecules, they are closely bound to each other, means they are strictly attached. Okay. When we come to the liquid, we find out there is considerable gap between the molecules. And when we talk about the gases, we found there very least number of molecules in the certain volume. Okay. Now, while looking on this diagram, we should be considering few of the things that are very important. The first thing is, as the molecules are closely packed, so why is it so? Means the reason behind the close packing is intermolecular force of attraction. Means the two molecules are so attracted with each other that they are getting stuck with each other, right? That means the intermolecular forces are higher. So IMF, intermolecular force of attraction, in the solid is greater than the liquid, is greater than the gases. That means the greatest intermolecular force of attraction with the molecule is in solids, right? That means these molecules have tendency to attract a thing with little bit more of the force. Okay. In liquid, the force is a little bit less, and in the gases, this force is almost negligible. That means they can flow wherever they want. It is almost negligible. Even you are cooking Maggi inside your house, the neighbors would know and they will come to your door asking for it. So the thing is, because the gases are having least or negligible intermolecular force of attraction, that's why they traveled so long and they make everyone aware. We can't trap the gases so easily. Next comes the intermolecular space. Intermolecular space. What is intermolecular space? The intermolecular space means the spacing between the molecules. So here the spacing would be least because they are closely packed. That means the space between the molecules would be least. And here the space would be little bit considerable, and here it would be maximum. That means the intermolecular spacing is least in solid while the greatest in gases. You get it? Next, here we can see that as the forces are greater here, that means they are attracting right away. So that means if you are having two contents, like let's say there is a liquid and along with that there is a solid. Okay, so we find out solid molecules are closely packed while the liquid molecules are not attracting them very much. So what will happen? The molecule that is nearer to the solid will be experiencing more attraction forces than the molecule of themselves. The molecule that is in vicinity to the solid will experience more forces of attraction with respect to its own molecules. And this tendency is called adhesion. Adhesion means sticking with other. Sticking with other. So that means this would go adhesion. What it is called? Adhesion. While these molecules of solid won't be leaving the solid and going into the liquid, reason is cohesion. They are more attracted towards themselves that they don't even consider the other neighboring molecules. So these particles are under cohesion. So it is not the basically game of density only, but if you like consider it very closely, you'll find out if you consider the density, it becomes handy. Means cohesion and adhesion has no direct relation with the density, but if you consider this logic, you will find out that it is applicable everywhere and almost every time it would be true. Okay. Now we have understood these three things. Now we can see that the maximum number of molecule in a given space is in solid, right? So that means what is density? Density is mass by volume. So what is density? Density is mass by volume. So that means if something has a greater mass in that definite space, that means its density would be maximum. Let's say you have three materials of this size. One material might feel lighter, one material might feel heavier, even though size are the same. The heavier material means they are having higher density, means higher number of molecules in them. The amount of substance is greater in them. Okay. So that means something that is having higher density means they are containing larger number of molecules in the given space, in the given volume. Okay. So density is mass per unit volume. This chapter, that lecture is actually a demo lecture. That means it won't be diving so deeper that we won't be considering like talking about the unit weight, talking about the packing efficiency and all that. But we would be considering all the important topics that are important for examination and serves its purpose as a demo video so that you can understand well how we are going to learn in the contents and the batches. Okay. If you want to know more about the batches, you have to stick along this course in this class. By the end of this lecture, we would be talking about everything that is needed to know. Okay. That is important for you to know about the batches or courses or how we plan all them. So the density is mass by volume, that you got clear. Now mass is kg and volume is meter cube. The SI unit is kg and meter cube. So the SI unit for the density would be kg per meter cube. So this would be its unit. Now comes the dimension. The mass can be represented as the m. The meter cube is actually the length and it is inverse. That means L minus 3. So this would be the dimension. Whether it is a scalar or vector, that means whether the direction plays any vital or sensible role. So it's no. Means in density, while considering density, direction doesn't even make a sense. Like if you talk about the masses, in mass what was there? Means the mass was like 3 kg of sugar. So if you ask east, west, upside, downside, so it doesn't make any sense with the mass. So 3 kg sugar, it's enough. But if you are talking about like I am walking, so which direction? The direction makes sense, no? Means it has some variable. So that means some quantity might have the direction sensible, that are called vector. Some they don't even make any sense with the direction. That means they are scalar. So density is itself a scalar quantity. A scalar quantity. Okay. Now next topic comes the relative density. What is the relative density? Means the density with respect to any other material. Relative density means the density with respect to any other material's density is called relative density. Now, if we compare this density with respect to water, it's called, so relative density means density with respect to other material, and if we compare it to relative density with respect to water, then it becomes a specific gravity. It's called a specific gravity. So as per our chapter, whenever there is relative density, that means generally specific gravity. So specific gravity G is equals to rho of the object upon density of the water. In almost of the cases, rho of water would be considered to be 10 to the power 3 kg per meter cube. That means whenever there is specific gravity, that means that object density would be G times of 10 to the power 3. So if you are given with the relative density and you want the density, if you are given with the specific gravity and you want the density, that means just multiply by 10 to the power 3. That is the density of water, and you will be getting the density of that particular object. Okay. Now let's come to the next topic. That means if we talk about the density, now comes the pressure. As I told you guys, like the mass and the force doesn't make sense in this chapter. That means instead of mass, we use density as analogous. Instead of forces, we use pressure as analogous throughout the chapter. Now, the pressure, what is pressure? Pressure is actually force per unit area. Force per unit of area. So that is pressure is equals to force per unit area. So the unit would be Newton per meter square. So the unit would be Newton per meter square, and the SI unit would be Pascal. It's called Pascal. Okay. So James Pascal was the person behind this Pascal's law. So to give him enough credit, the pressure unit is credited to him as a SI unit. So that means Pascal is the SI unit of the pressure. Next comes the thing that you should know, like if their area is the least, the pressure would be maximum. If the area is the maximum, the pressure would be least. That means area is inversely proportional to pressure. That means if I have something that has quite larger area, that means it won't be making that much pressure. But if the sharp edge is through this area, that means we would be experiencing much more pressure and hence the piercing. So while piercing anything, we need the pressure. That means the minimum area should be there. Hence the needle, the knives, they are made so sharp. And wherever the pressure is to be least, like the shoulder bag straps, they are much more wider to minimize the pressure, because the area maximum means minimum the pressure. So instead of thread in a fashion, you should be using the bags that have wider shoulder, right? So that you experience least of the pressure. Now here, this pressure that we defined here is actually from the sense of the mechanics, not from the sense of the liquids. Like here, the liquid, in liquid we can't apply the force, na? If you try to apply the force, the liquid will disperse because it has no Young modulus. That means it would displace from that place and you would be ending with the solid ground, not the fluid. That means here the density should be in terms of density, and the pressure should be by its own weight. Okay, so by its own weight, that means the force that we should consider should be the gravitational force, and that is called its weight. Now, as we already studied, the density is equals to mass by volume. So that means mass must be equal to density into volume. Mass must be equals to density into volume. So here we should be putting like the pressure is equals to force upon area is equals to mg by A and is equals to rho into V into G by A. Okay. Now the volume can be considered as, because here is the area of cross section. The area of cross section into height, that is volume. So it can be written as rho A H G by A. The area of cross section cancels out and you get rho G H. That means the pressure due to the fluid is actually rho G H instead of using force upon area, because force you cannot consider, you cannot calculate, you can't even find. Whenever you apply the mechanical things in the fluid, you find yourself as a failed person. So here, instead of doing that, we should be considering the density. Okay. So rho G H, the pressure under the fluid would be rho G H. So fluid pressure is what? Rho G H. Now there are two types of pressure. One pressure is called gauge pressure. Gauge pressure. Gauge pressure is actually the net pressure. Net pressure without considering atmospheric pressure. without considering that atmosphere. It means, let's say I am applying the pressure on this pen. Okay, so that means there would be atmospheric pressure from upward also, means atmosphere is also, and from the downward is also atmospheric pressure. It would actually cancel out. The gauge would only show the pressure that you have applied and leaving out the atmospheric pressure. Okay, and what is absolute pressure? Absolute pressure means gauge pressure with atmospheric pressure. Gauge pressure plus atmospheric pressure. Rho GH plus PA. Okay. Now let's do the first question of this chapter, that is example number 1. So here it is general mechanics example, that is two thigh bones, that is femur, each of cross-sectional area is this. The longest bone of our body is femur, you should remember that, and strongest also. So area is 10 centimeters square, support the upper part of human body of mass this. So here the force is due to gravity, that is its weight, any mass into g. Okay, the force, gravitational force is called weight. So weight is m into g, that is 40. Let's consider that as g is equals to 10 meter per second square. Gravitational acceleration, so it would be 40 into 10, that is 400 Newton. Now the area is given as 10 centimeter square, converted to the meter square, that is 10 into 10 to the power minus 4 meter square, that is equals to 10 power minus 3 meter square. Okay. Now the pressure is equals to force upon area. Force is 400 upon 10 to the power minus 3, that is 400 into 10 to the power 3 Pascal. This 10 power 3 is called as kilo. 10 power minus 2 is called centi. 10 power minus 3 is called milli, while 10 power plus 3 is called kilo. Okay. And 10 power plus 6 is called mega. 10 power minus 6 is called micro. The same way it's called kilo, that is 400 kilopascal. You should not be comparing this answer with the NCERT solution. Reason, they have considered the G to be 9.8 and we are taking 10 as per our exam scenario that we need. Okay, that means we want the approximation. We want to be having the calculator. That means we should be approaching the values that are quite easier to calculate, and then we would be resembling it with the, comparing it with the options that are provided, and hence we would be jumping to the solution or the conclusion. Okay. Next comes the Pascal's law. Pascal's law suggests, first of all, Pascal assumes few of the things like gravity is negligible, like material is incompressible, like it's ideal fluid and so, and then gave some of the laws. That means if a fluid is contained in enclosed chamber, the chamber is enclosed and the fluid is contained in it, then if you apply any pressure to throughout the body anywhere, that pressure would be transferred to the throughout the body without any loss. That means the pressure is equally distributed throughout the surface wherever you go. That means pressure at one point must be equal to the pressure at second point. If the fluid is enclosed, fluid is in enclosed vessel. So if you apply any pressure, that pressure will go throughout the surface. Okay. Now, pressure 1 is equals to force upon area. Pressure 2 is equals to force upon area. So it is F1 A1, F2 A2, right? Now, if you want the F1, the F1 would be equal to A1 by A2 into F2. That means in such a type of question, wherever the force is being asked, you should be getting the ratio of the areas. The ratio of the area will tell you what is the multiplication of force, means how many times the force can be going to be multiplied or divided. So here, if the area is the least, that means the force should be least. If the area is least, the force should be least. If the area is highest, the force applied there would be highest. So lower the area, lower the force. Higher the area, higher would be the force. So here we can see F1 and A1. F1 is actually acting on A1. So if A1 is least, the force would be least. If A1 is highest, this force would be going to be highest. Okay. So you have to understand these things. We will be doing some examples to know that. Okay. Let's come to the example number 9.5. What about the 9.2, 9.3 and 9.4? We will be coming to that later in this same lecture. Now, two water-filled syringes of different cross sections are connected by a rubber tube. So two cross section syringes are there. Let's say this is syringe, okay, and this is the another syringe. Let's say its diameter is a little bit thinner, okay, and they are connected with the pipe. They are connected with a pipe. This makes a lot of sense that because throughout the vessel the liquid is enclosed, that means the pressure over here should be equal to the pressure over here. So P1 must be equals to P2. Okay, that's clear. Next. Now they are giving the pistons have the diameter 1 centimeter and 3 centimeter. So it has 1 centimeter and it has 3 centimeter. See, the larger the surface area means the larger would be force. Lower the surface area means the cross section area, lower would be the force. Now let's calculate the area ratio. Let's say it is F1 and A1. Okay, so A1 would be what? Pi r square, that is 3 square, that is 9 pi into 10 to the power minus 4. And A2 would be what? 1 centimeter square, that is pi into 10 to the power minus 4, that is meter square. Now we know A1 by A2 would be equals to 9. A1 by A2 would be equal to 9. So A1 is the largest, means F1 would be the greatest. So here the F1 would be, as we know that ki F1 is equals to A1 by A2 into F2, right? That means this is 9. So F1 is actually 9 times of F2. So whatever the force you apply over here, you would be experiencing 9 times of that force over here. Okay, that means let's find the question. Find the force on the larger piston when 10 Newton is applied on the smaller. So here the force is applied is equals to 10 Newton. So here it would be 9 times of 10, that is 90 Newton. 9 times of F2, that is 9 into 10, that is 90 Newton. So it would be 90 Newton. Now, what they are asking, if the smaller piston is pushed by 6 centimeter, then how far the larger piston would be moved? So we must be knowing that our water is fixed. That means the volume is fixed. If the volume is fixed, that means, let's say the piston moves over here is this area into this distance D1. And here, this is the area A2 and this distance that is moved, it's let's say D2. So we know that ki A1 D1 must be equal to A2 D2. Okay. So we can say that ki A1 by A2 into D1 is equals to D2. Now they are asking us ki smaller is moved by 6 centimeter. Smaller is which one? Smaller is actually D2. So D2 is equals to A1 by A2 into D1. Okay, that means we have to, no, smaller is given. The smaller is D2, na? But we have to calculate D1. D1 is equals to A2 by A1 into D2. Yeah, that's it. So it is 1 by 9. And D2 is, if you put it in 6 centimeter, you will get the answer in centimeter. So that would be 9 times of it, that is 0.67 centimeters. Okay. So means wherever you find the Pascal law, you must be understanding two things clearly. First, the pressure is same, that is F1, F1 by A1 should be equal to F2 by A2. And here the logic or the trick is you first calculate the area ratio. Once you get the area ratio, everything becomes the same. So here, instead of doing this, you just calculate A1 by A2 is equals to whatever the unit it is, R1 square by R2 square or R1 by R2 whole square. So here it was like the diameter ratio was 3. No? So 3 ka square, that is 9. The ratio must have been 9. Instead of calculating this much, you must have jumped the calculation like ratio of the radius, then square it. Take the ratio of the radius and square it. Take the ratio of the diameter and then square it. So whether it is diameter or the radius, just make the ratio and square it. The ratio is 3, square that is 9. So A1 by A2 will be 9. Let's move to the next question. That is example number 9.6. In a hydraulic car lift, compressed air applies a force F1 on a small piston of radius 5 centimeters. The smaller radius, let's say small radius is smaller. This pressure transmitted to a larger piston of, let's say it's capital R. So we know that the ratio ratio, that is A by capital A is equals to small r by capital R ka square, that is 5 upon that is 15 square, that is 1 by 3 square, that is 1 by 9. So we got the area smaller upon larger. Okay, and we can see that key F1 is for small, that means F1 compared to A1 small a. Now we know that F1 by small a is equals to F2 by A2, that is capital A, and this pressure is transferred to large pressure. If the car has to be lifted, so compressed air applies a force. So compressed air applies force F1. This is the force that we are going to apply through the compressed air, and this is the force due to the car. Okay. Now they are asking to determine the required force F1. They are asking to calculate F1. F1 would be equal to A by A times of F2. So A by A is actually 1 by 9, and F2 is what? The weight of the car. So weight of the car, F2 is equals to weight of the car, that is mg. M is to be 1350, right? Let's suppose G to be 10. So we got 13,500 Newton, right? Now 9 ones are 9, 9 fives are 45, 00, that is 1500 Newton. So the compressed air must apply the force around 1500. Now if we consider the G as 9.8 instead of 10, you will find out this force would be a little bit lower than that. That means if you are given with the option, you should compare the closest value that is lower to this should be your answer. If the answer are so close, options are so close given in the question, then you should be using the value of G as a 9.8, or else always try to use, if the options are distinct and little bit difference in them, considerable difference in them, then you should be always considering G to be 10. Okay. So we got that, and let's move the next one. Now comes the fluid pressure. We know the fluid pressure. What is fluid pressure? Pressure due to fluid, and that is equals to rho GH. Pressure due to fluid is rho GH. We have already derived that. Now, if you consider like atmosphere to be this, okay, and let's say this is ground. So in fluid pressure, this H is from distance of the surface from the free surface. So here H is the height of free surface. Never get confused with that. Free surface from the base. Let's say we want the pressure calculated to be here. Then whatever the reference point you are considering, this would be the H. Okay. That means from the reference point. Okay. Or analytical point, whichever point you are to calculate, the H would be considered from that place to the free surface only. That means this would be H, this would be H. Okay. You won't be calculating the H to be this. No, it's always from the top. That is the free surface. Okay. Now the atmospheric pressure would be like P atmospheric equals to rho of air, because the gases are there, into G into the height of atmosphere. And if you just make it equivalent to 1.0 and 10 power 5 Pascal, that is the atmospheric pressure. So this H would be calculated. This H would be easy to calculate. Now let's go talk about the pressure due to the lake. This is the lake, and there is a diver over here. Now they are asking how much pressure is here. Let's say it is 10 meter deep. So below 10 meter, what is the pressure? So pressure at 10 meter should be equal to the pressure that is applied from the environment, that is P atmospheric, plus the pressure due to fluid, that is P atmospheric plus pressure due to fluid, and that would be equals to 10 to the power 5. Always take it to be 10 power 5. Why? Because 1.01 doesn't make that much sense. So 10 power 5 can be considered, and then take the options whichever is closer. Now plus pressure of the fluid is rho GH. Rho of water is 10. This is rho GH. Now 10 power 5 plus rho is 10 power 3, because it is a fluid of water. Let's say it is water. Let's say it is water. And G is 10 and the height is 10. So this is 10 power 5, that is 2 into 10 to the power 5. So this would be the pressure at 10. Means if you get below 10 meter, just 10 meter below in the river, you will find out the pressure due to the fluid is equivalent to the pressure due to the atmosphere. Means it's equivalent to the atmospheric pressure. Okay. So that means let's do this question. Then we will be talking about the barometer. Now, the area of cross section of a wider tube shown in the figure is 800 centimeter square. So the area over here is 800 centimeter square. And the mass that is lying over here is 12 kg. Placed on the massless piston, the difference in height of the level of water of two tubes will be. So they are asking about what is the value of H. So we know that, let's say it is P1, it's P2. Because the chamber is enclosed, that means P1 must be equal to P2. The P1 is equals to the pressure due to this column of fluid that is balancing this column. Okay. It's acting kind of like a manometer. That means you should be considering a line below which the liquid is same. Okay. Then afterwards, the above would be the same pressure. So if you find a liquid that is homogeneous throughout the level in both the limbs, then you must be knowing that above that the pressure over here or here would be the same. That means pressure P1 should be equal to pressure P2. That means rho GH is equals to P2. P2 is what? The force F2 upon area. F2 is what? mg upon the area. Mass is 12, that is 120. 12 into 10 means G is considered to be 10. Area is 800 centimeter, that is 10 power minus 4 meter square. Now, rho GH, that is 10 power 4, 10 power 3 into 10 into H is equals to, get to here, that is 120 upon 800 into 10 to the power plus 4. Now, 1 0 cancels out. Now, 10 power 4, 10 power 4, that is cancelled out. The H is equals to 12 upon 80 meters. Let's make into centimeter. That would be into 100 centimeter, right? That is 1200 upon 80. So 1 0 cancels out. 8 1s are 8, 8 5s are 40. So that is 15 centimeters. So this column height should be 15 centimeters. So whichever the question is given, wherever the question is given, if it look like a manometer, yeah, YouTube manometer, you must know, you have to find out the level at which the bottom liquid is homogeneous, above which the pressure must be identical as per the Pascal's law. And when you compare those pressure, if the fluid is there, calculate the fluid pressure. If the material is there, calculate the material pressure, and then equate them. Whichever is unknown, that would be under your eye. Now, what is the pressure on a swimmer? This is the example number 2. So we have done 5, 6, 1, and this is 2. So 3, 4 is missing. We would be considering that in the later on the lecture. What is the pressure on the swimmer? That is 10 meter below the surface of a lake. So below the surface of a lake, that is 10 meter below. So here is the swimmer. Now you must be understanding, like it is 10 meter and here it's 1 atm atmospheric pressure already there. The absolute pressure on this person must be equal to the atmospheric pressure plus the fluid pressure. Atmospheric pressure considered 25, and this is actually rho GH. We have already done that actually. That is 10 power 3 into 10 into 10. That is 2 into 10 to the power 5 bars or Pascal. Okay, you get it? So here it's the absolute pressure that you must be calculating. So anything that is below the free surface, that means rho GH will be the pressure due to the fluid, and atmospheric pressure is everywhere. Now come to the next one. Example number 3. The density of the atmosphere at sea level is this. Okay. Assume that it does not change with altitude. Then how high is the atmosphere? So let's say the atmosphere is up to this level and this is our ground surface and this is the height. Now the pressure over here, P at ground, must be equals to rho GH, rho air, and the height of air column. Now P atmospheric pressure is actually given. No, it's not given, but we assume it to be 10 power 5. Okay. Rho atmospheric is given like 1.29 or just take it as 1.3, into G, take it to be 10, and H, that is the one that we have to calculate. So H would be equals to 10 to the power 5 upon 13 upon so it can be written as 100 into 10 power 3 upon 13. (7.6) into 10 power 3, around 7.6, or then that can be calculated as 7.6 kilometer. 10 power 3 becomes kilo, and then meter, kilometer. 7.6 kilometer might be the height. Okay. Yeah, that is the way of doing it. So that means whenever the pressure is given, okay, let's say P, and it is given as 1 atmospheric equal to 10 to the power 5 Pascal. 10 power 5 Pascal. Now, at depth of 1000 meter in the ocean, calculate the gauge pressure, calculate the absolute pressure, determine the force. Now, let's say gauge pressure. So, gauge pressure, P gauge is equals to rho GH, that is equals to rho is given 10 power 3, it is 10, and the height is 10,000, that is 10 power 3. So it would be 10 power 7. Instead of doing 10 power 7, just make it like 10 to the power 2 into 10 to the power 5. That is equals to 10 power 2 ATM or 100 ATM. 100 times of atmospheric pressure. This is the atmospheric pressure. Now, P absolute is equals to P atmospheric plus P gauge. That is equals to 10 to the power 5 plus, or that is 1 ATM plus 100 ATM. That is equals to 101 ATM. Or if you want in Pascal, that is 10 power 5 plus 10 to the power 2 into 10 power 5. That is 101 into 10 power 5. Now determine the force on a submarine window of area this much when the interior is maintained as a atmospheric pressure. So interior is maintained atmospheric pressure, means inside to out direction. Inside out the pressure is, let's say it is a submarine window. So inside, let's say it's inside. So inside there is already 1 ATM, and outside this is the gauge pressure and then atmospheric pressure. So atmospheric pressure outside and the inside would cancel out each other. That means the pressure acting on the window would be the gauge pressure. So pressure on the window, P on window is equals to P gauge pressure. Okay. Now pressure on window is equals to, now they are asking the force on window. So P is equals to F by A, or the force is equals to P into area. So pressure, gauge pressure is given as 10 to the power 2 into 10 to the power 5, and area is what? Area is 20, that is 400 centimeter square, 10 power minus 4. So we have it's 100. Let's do that. 10 power 3 into 10 to the power 4 into 400 into 10 power minus 4. Just solve it and you will be getting the answer. So 400 into 10 to the power 3 Newton, or 400 kilonewton. 400 kilonewton. Okay. So we have done the third part, that is C. This was B, this was A. Right. Next comes the equation of continuity. What's the equation of continuity? Means whenever the mass is entering somewhere, that mass is conserved, right? So that means the mass must be leaving out of it. That means if there is a continuous flow of mass from one end and there is continuous exit, there must be continuous exit from the other end if there is pipe. So that means mass, and if the liquid is incompressible, that means the mass entering per second must be equal to the mass exiting per second. That means let's say here the mass is exiting m1 and exiting m2. So that means m1 per second must be equal to m2 per second. So here the mass is density into volume. So rho1 v1 upon s is equals to rho2 v2 upon s. Now it's called area into the length. Volume is area into length. So area rho1 a1 length upon s is equals to rho2 a2 L2 by s. This is velocity, length of flow. So rho1 a1 v1 must be equals to rho2 a2 v2. As if we consider like the fluid is incompressible, that means the density won't be changing. Means the rho1 is equals to rho2. Means the same fluid is entering and the same fluid is exiting. That means the density is same. So if we consider the density to be same, then a1 v1 must be equals to a2 v2. So this is the equation of continuity. It's based on the conservation of mass. The law of conservation of mass. It is the output of the law of conservation of mass. Mass is conserved. That means area into velocity must be constant. So if the area into velocity is constant, so that means area is inversely proportional to velocity. If area is inversely proportional to velocity, means larger the cross-section area, lower would be the flow. Means velocity. If the cross-section area is smaller, that means the flow rate would be higher. That means velocity would be higher. So here the V1, here let's say it is V1 and it's V2. Let's say it is V1, A1 and it's A2, V2. So here we can see that the A2 is smaller than A1. So if area is smaller, that means velocity must be higher. That means V2 would be greater than V1. Okay. So continuity equation just gives us the relation between the area and the velocity only. Okay. If we gone through that, we should be jumping on the Bernoulli equation. What is Bernoulli equation? Bernoulli says that the net energy. So if we talk about the energy is conserved, Bernoulli is based on conservation of energy. Law of conservation of energy. See, if the energy is conserved, let's talk about the fluid. In fluid, we can't be considering the masses. That means we should be talking about the pressure and the density. So here we don't have the concept of just judging the energy. So what we we set a definite volume of the box, the masses. That means we should be considering the per unit volume, means energy per unit volume for a particular volume. So energy for a volume of water, that means energy per unit volume is constant. So energy per unit volume is constant. Total energy per unit volume is always constant. So net energy per unit volume is constant. Energy might be of several kinds, like the pressure energy. How many energies are there? E total is equals to pressure energy, or let's call it EP. Then let's call it E kinetic, then call it E potential. Okay, three types of energies that we consider in the Bernoulli equation. That is pressure energy, kinetic energy, and the potential energy. This potential and this is pressure. Okay, now let's do that. So the pressure energy must be equal to the work done, means energy is the capacity to do work. So if you want to know something, the energy must be equivalent to the work due there. So if we have no formula or idea of the pressure energy, so work done by the pressure is called pressure into volume. Okay. Now what is kinetic energy? That is half mv square. And what is potential energy? That is mgh. These are the things that we have already studied. Now let's come to the next part, that is ET by V. So what would be ET by V? So divide by volume, divide by volume, divide by volume. Let's come to the next part. It is velocity actually. Now volume cancels. That means pressure plus the mass can be written as a density into volume. So it would be half rho V square upon V plus rho V GH by V. Now cancel out the volume. Now you get like P plus half rho V square plus rho GH. So this is the total energy per unit volume. So it is the total energy volume per unit volume and it must remain constant. And as we know that the energy per unit volume is actually somehow getting to be pressure. So energy per unit volume actually gives the unit of pressure. So whatever the unit you check out, everything would be in terms of pressure. That means Pascal. Next comes another thing, serious thing. If we divide it by rho g, everything would be heads of it, like meter of energy, like 10 meter of energy, 2 meter of energy. So meter is not a unit of energy. How we can do that? We convert in form of the head. So what is head? Head is dividing it by, so the head would be also constant, P by rho g plus half or V square by 2g plus h. So everything is in meters, constant. So this is also the Bernoulli equation, and this is also the Bernoulli equation. It is energy per unit volume, that is energy per unit volume, and that is pressure. And here, if we divide by rho g, V rho g, that is mg. See, here we have already divided by V. So if we divide the energy by force, so what we get? Energy upon, the gravitation force mg, that is E upon rho Vg. And if it was pressure energy, so pressure was PV upon rho Vg. So Vv cancels out, that is P by rho g. Now if it is kinetic energy, half mv square, convert it to be rho m, then v square upon rho Vg. So rho V cancels out, that is V square by 2g. Now, if we divide by rho g h by rho g, so that would be actually h, that is potential energy head. So we can also calculate these things in terms of head. How we know that? Actually, whenever there is a pipe and inside there is a pressure, right? So if we just put a hole and then pipe on it, you'll find out the water rises up to a certain level. And the rise in that certain level is actually measuring the pressure inside the pipe. So if there is any pipe flowing from A to B and you just make a column on it and it is flowing from this side to this side, so whatever the pressure is there would be indicating a level of certain height, and that is actually the pressure head, rho g h. If you calculate this rho g h, you will find out the pressure in difference inside the pipe. Okay. So that means the pressure can be also, or energy can also be measured in terms of heads, and energy can also be measured in terms of pressure. Energy per unit volume is somehow the pressure, right? Now let's come to the next question. Next thing, like this is the question. Water flows through a frictionless duct with a cross section varying as shown in the figure. Present pressure P at points along the x-axis represented by. So see, here we find out this, let's say it is A1, let's say it is A2. The pressure over here is P1, let's say it is P2. The velocity over here is V1, the velocity over here is V2. The height from the datum line here and here, let's say it is the reference line. So we see that the height is same from the both points. So as per the Bernoulli equation, the P1 plus half rho V1 square must be equals to P2 plus SH is equals to P2 plus half rho V2 square plus H. HH cancels out. So P1 minus P2 is equals to half rho V2 square minus V1 square, right? This is the thing. Now let's see. As we know that area 1 is greater than A2. So that means velocity at 1 must be less than V2. How? Because we know that as the area is higher, the velocity is lower as per the equation of continuity, because AV is equals to constant. So if the area 1 is higher, that means velocity at 1 is lower, V2 is higher. As in this equation, we can see that this is higher. So as V2 is greater than V1, so this equation must be positive. That means it is greater than 0, or P1 minus P2 must be greater than 0. And if P1 is greater than 0, that means P1 should be greater than P2. So pressure at point 1 or point A is actually greater than point B. So initially the pressure over here was larger and the pressure over here is smaller, because that pressure is being converted into the kinetic energy. So this pressure energy that was here being converted into a kinetic energy, and the pressure drops. So if there is a velocity, higher velocity, that means there would be lower pressure. So if there's a book and you are just making yourself blow a air on it, you'll find out the velocity of air as increases, the pages would be flipping above. How? Because the pressure above would be reduced. So as the velocity increases, the kinetic energy increases and the pressure energy decreases, because the net energy must be constant. So to make the whole energy constant, if one is increasing, the other must be decreasing. You get my point? Like if we have three energies, like pressure energy, kinetic energy, and the potential energy. Okay. Now let's the total energy be constant. Let's say it is 100. So, and it is like 20, 30, and 50. Now, for some instance, this kinetic energy increasing, let's say it is becoming 70. So if kinetic energy became 70, that means the rest must be reducing. So the net will always be 100. So either the potential energy would decrease or the pressure energy would decrease. So to compensate this 20, either the pressure must be 0 over there or the potential must be compensating the value. But say if the horizon is flat, that means there is no upside or downside, means no gradient is there, means the potential is same on the both level. This is horizontal line. So this PO would be same, that is it is remaining to be 50. That means pressure would be becoming 0. If it is getting 70, so it would be 50, so it would be 10. So it cannot be 70. It can go up to maximum 50, because the net must be 100. The maximum limit is 50. So it would be 0. Okay. 50, 50. So it cannot. So if it is horizontal line, so it would be 50. And if it is 50, then it would be 50. Because as I told you guys, the kinetic energy increased to 50. That means the pressure must be 0. That means whatever the object over here was to be pushed down to this side. Let's say you are standing on the platform. Train is approaching and passing in front of you. So you'll find out the train is moving with a large velocity. The train moving with a high velocity means there would be higher kinetic energy. Both the levels are same. You are on the platform and that train is going on a smoother scale. That means if we talk about the platform and the railway station, railway track, there is no such a big difference. The difference is of kinetic energy. So if the kinetic energy is increased over there on the railway track, that means the pressure is reduced. And if the pressure on the railway track is reduced, that means the pressure at you is already that it was before. So that means you are at higher pressure and the track is at lower pressure. So that means you would be pushed on the railway tracks. So that means whenever the train is approaching, you should always stand before the yellow line. You shouldn't be just trying to touch the train, because if you do so, you will find out a pressure of push on you, and you will find out yourself to be wandering on the railway tracks. So that means whenever there is an increase in any of the energies, the rest energy would decrease themselves so that it compensates it and makes the energy remain constant. Okay. So what is the graph? So here we can see that P1 is greater, means the pressure here is greater and the pressure here is smaller, means larger to smaller. So larger to smaller, P is larger over here, is smaller. Here P is constant, here is constant, increase, decrease. Here it's increasing. So only the first option is correct. How the curve is changing with the distance, that is not the matter of here, because it would become very complicated right now, as in terms of velocity, how it's changing with the direction, this distance. So distance is not in the equation, no? So if we want it to be per unit distance, that means we should be dividing it by distance, whatever the pressure is there, per unit distance, and then we would be plotting the graph. But only thing is sure that the P1 is greater than P2, that means it should be higher, and then later on it should be lower. So it's higher, later on it is lower. That's it. Let's move on to the next question. Next question is, water having density rho is flowing steadily downward in the vertical tube as shown. What is the relation with the pressure at point A and B? Means where the pressure is greater, where the pressure is lower. Let's talk about the point A. And let's area of cross section A1, velocity V1, and the pressure P1. And here, let's say the area is A2, the velocity is V2, and the pressure P2. As from the diagram, we see that, as we know that AV should be constant. AV must be equals to constant. So larger the area, lower would be the velocity. So larger the area, lower velocity means here the velocity is higher, means V1 must be greater than V2. First thing is sure. First thing is sure. Now, if we talk about the height from the below, from the bottom, now let's talk about the Bernoulli equation. So it's P1 plus half rho V1 square plus rho G HA, height of A, is equals to P2 plus half rho V2 square plus rho G, it's 2 na, so it's B, HB. Now, you must have to remember the pressure that we already discussed about that, like in the previous slides, that was rho GH. And here in rho GH, this H is actually height from the base, means this is the height. But no, this is the height. If we talk about as a pressure. Now, if we talk about like mgh, that is potential energy. In potential energy, it is gravitational potential energy. And in potential energy, it is actually calculated from the ground. So it is H. It is H. Do you get my point? Means if the mgh becomes rho gh, means the potential energy, in potential energy, the height is from the base, while in the fluid pressure, the height is from the top. So here it is potential energy height, na? Rho gh, it is derived from the potential energy mgh by volume, hai na? Means potential energy per unit volume came to be like a pressure. But this height is from the base. So the height over here, so height in energy, it potential energy. So if you are considering like pressure, it is pressure. So for pressure, it's always from the free surface. And for energy, that is potential energy, the height must be calculated from the bottom. mgh means if you are rising something, you are working against gravity, that is gravitational potential energy. And the height is from the bottom. So here in the equation, this HA, see HA, this is HA. And let's say this is HB. So clearly we can see that HA is greater than HB. Okay. Now let's solve it. So we can see that P1 minus P2 is equals to half rho V2 square minus rho V1 square. Okay. Next is equals to plus rho GHB minus HA. See, HB is less. Less minus more means it is negative. It's going to be negative or less than 0. Let's talk about this. As we know this, V1 is greater, V2 is smaller, and we are subtracting greater from the smaller. That means this is also going to be negative. See, greater is being subtracted from the smaller. V2 is smaller. Okay. So if you subtract larger number from the smaller number, you get negative. So these both are negative, means total is negative, or the whole is getting negative or less than 0. That means P1 minus P2 is less than 0, or P1 is less than P2. So P1 is less than P2, or P1 is what? PA. That is PA less than PB. PA is less than PB. This question seems so easy, but so difficult at the point of concepts, like the height that you took, whether it should be from free surface or from the bottom. It should be from the bottom because it's a potential energy, rho GH. Here it is potential energy. Potential energy, we consider the height from the base, not the top. Okay. And if we talk about the fluid pressure that we discussed, rho GH, that rho GH was fluid pressure. So in that, fluid pressure was considered to be, the height was considered to be from the free surface. It's by accident everything became pressure, but it is the energy. So while calculating these, you must be keeping in your mind that these are energy per unit volume. Don't be confused it with the pressures. Okay, so it is a pressure energy, it is this and this and so on. Okay, so these are the energies, and in turn they give the pressure by chance. Okay, let's move to the next one, that is Reynolds number. What is Reynolds number? There are several of the number in this fluid, that is Reynolds number, Weber number, Mach number, and a Froude number. So these numbers have some roles in that. So Reynolds number has a role in which by using the Reynolds number we can determine what type of flow it is. Means whether it is a laminar flow, means sheet by sheet. Everything is steadily flowing sheet by sheet, or they are just turbulently or vigorously flowing, everything is mixing with each other. So lamina by lamina, that is sheet by sheet, that is called streamline. So every line is streamed in direction. No line is breaking. Means if you just put a die in that, the die thread would be straight. That is streamline. Okay, and sheet per sheet is called laminar. And somehow the laminar and streamline, they both happen simultaneously. Means if the flow is laminar, that means it is a streamline flow. Or if it is streamline flow, it is considered to be laminar flow. Okay, so flow is sheet by sheet, sheet by sheet. The bottommost sheet is actually at rest. The topmost sheet is actually at the maximum velocity, if the air velocity considered to be negligible. Okay. Now, understand this thing. Key, when we try to flow, there is something that is hindering it. And what is hindering it? There is a kind of friction acting it. So friction between these laminated layers, there is a friction hindrance. They resist the flow. So this phenomena of resistance inside a fluid is called viscosity. So what is viscosity? The resistance of the flow is called viscosity. As we get resisted while walking due to the friction, the same way there is a resistance in the fluid while flowing. Okay, so this is the friction force, and there the friction force is known as viscosity. So analogous of friction is viscosity. The units are not same. Okay, now understand this. The Reynolds number is actually inertial force upon viscous force. Then there is a Froude numbers. What is Froude's number? This is equals to inertial upon gravitational force. Then there is Weber number, and that is actually inertial upon tension force. Then there is Mach number, that is the velocity per unit, the speed of sound or sound velocity. So velocity with respect to the sound velocity is called Mach number. Okay. Now what is inertial force? That is ma, mass into acceleration. Inertial is mass into acceleration. And viscous force is 6 pi eta rv, 6 pi eta rv and so on. Or we can calculate the viscosity by using different things, and after all we would be getting, like in terms of rho, we would be getting like rho v, the diameter, upon mu or the eta, whatever the symbol you use. So Reynolds number becomes rho v d by mu, where mu is the viscosity, that is dynamic viscosity. Now here we see that if the Reynolds number is less than 2000, it is actually the laminar flow. If it is between 2000 to 4000, it is the transitional flow. If it is greater than 4000, it is the turbulent flow. Means on the basis of Reynolds number, we can understand the type of flow. And something more, like how the type of flow can be affected by the parameters. So we can see the flow can be affected. Means if we want a better flow, means a streamline flow, the Reynolds number must be lower for a streamline. If the Reynolds number is least, there would be streamline flow. And to make the Reynolds number least, we must have the viscosity highest, the diameter of the pipe to be lowest, the velocity of the flow to be lowest, and the density, if it is water, we can't do that anything. Or if it is anything that has the lower density, then it would be the better. Means if we want the laminar flow, we must have high viscosity, lower density, lower velocity, lower the diameter of the pipe. So low diameter, low velocity, low density and high viscosity means the best type of laminar and streamline flow. You get it? Now, I have also included all the numbers. Island number, it is also the pressure and upon inertial, that reverse of it, and the rest are inertial upon something. Webb, in while the, like, there is a trick to remember all these. Like, gravity was considered to be fraud in the time of the discovery of it. So it's all you can understand is fraud. So it's a fraud number, means inertia upon gravity, that is fraud. Then Webb, there is a spider web and Webb has the tension in it. So it would be inertia upon tension force. The Weber number is inertia upon tension force. Reynolds number is actually flow, and flow means the relation to viscosity. That means inertia upon viscous force, inertial upon viscous force. What is inertial force? That is ma, mass into acceleration. Now, let's come to the dynamic lift. See, dynamic lift means if we have aerofoil. What is aerofoil? Aerofoil. What is aerofoil? Means designing a structure in such a way that its upper end has a larger length than the lower end. Okay. So if you design something like that, you will end up having something very interesting. How? See, if there is a wind over here and this plane is traveling in front of, through it, no? So there would be relative speed. Well, let's say there is no wind velocity here. And once you start driving a bike, you find out there is velocity inside your air, means relative velocity would be there. The speed with which you are driving the bike, the same speed we would be experiencing the wind to be flowing from us. The same here. So whatever the speed of plane, that would be the velocity below. And there would be much more higher velocity above. Why? Let's say it is VH. And this is V below. So VH should be greater than V low. Why? Because it's a character of aerofoil. Means the distance over here is low and the distance above is high. All the plane is moving with the constant velocity, no difference from above and below. The air relative speed of air must be higher because it has to travel larger length in the same time. While below, it has to travel the same length. Means the plane velocity would be this. So V low is actually V of the plane. But V above is actually greater than that of plane because it has a larger length. And we know that if it is moving on a horizontal plane, let's say it is moving on a horizontal plane, means height is same. No drop or flight is there. So that means P1, like P high, P below, let's say it is P high, okay, plus half rho VH square is equals to P low plus half rho V low square, right? Now PH minus P low would be equals to half rho V low square minus VH square. We know that velocity at the lower is higher. No, velocity at the higher is lower. Means it is having, means VH is higher than V low. So VH is greater than VL, means it would be negative or less than 0. So PH minus PL would be less than 0, or PH would be less than PL. Means the pressure over here would be higher and pressure above would be lower. And we know that if the pressure difference is there, there would be flow. The substance would move along the pressure difference. So higher pressure below and lower pressure above means the plane would lift up. The plane would lift up. So this aerofoil ensures that this aeroplane would lift up. The same goes with the running track or Formula 1 racing cars. They design in such a way that the phenomena is reversed. Means the car shouldn't lift up. They should remain in the position. That's why they have the tails in the before, by the end of the car, there is a tail. So that tail ensures that the car remains on the ground, doesn't flow like a plane. Otherwise, there would be no grip, no control at all. Okay. So this aerofoil, the velocity difference over here creates the lift. And if creates the pressure difference. And if you want the lift force, so what is lift force? That is, let's say it is higher. P low minus pH. This is the pressure, that is the plane lift pressure. Plane lifts by this pressure. Now, the force of lift would be equals to pressure into area, because pressure is equals to force upon area. So P lift, LF, let's say left, otherwise you will confuse with the low or high. PLF, that is equals to PL minus PH, that is pressure difference, into the area of the base and along with the wing. Even the aeroplane itself has an aerofoil design, and then the wings also, the cross section is also in the design of an aerofoil. Okay, so both are in the design of aerofoil. Means if we have the area of the wings, that means we can calculate the lift up force. Okay, and this, how we could go to this part. So if PL minus PH, देखो PH minus PL is given this. So if you want to calculate PL minus PH, just put a negative sign on both sides. That means this PL by minus PH is equals to half rho VH minus VL square, or VH square minus VL square, because VH is greater. Because this pressure difference is this, or the lift force would be equal to half rho VH square minus VL square times of area of the wing or the base, whatever it is. And that area is total area, not the one wing or a part of wing. It is the total area that is in the action of aerofoil. Do you get it? So it is Bernoulli theorem. So plane fly on the basis of Bernoulli's theorem. Next comes the viscosity, how it is. So until now we have discussed like some of the basic things, but here comes the thing that is conceptual, like capillarity, surface tension, viscosity, surface energy, stored energy in the surface, that many things. So before starting that, we must be understanding the viscosity. What is viscosity? We know that the water flows by layer and layer and layer and so on. So the water layer, that is the lower bottom, it should be stagnant, means it shouldn't be moving with any velocity. If it is moving, that means it would erode the soil bed, and hence there would be continuous deepening of the canals. It doesn't happen so. That means the lowermost lamina of the water body doesn't flow actually, and then there is a relative flow, and the topmost layer flows at the maximum. If there is air wind, that means just below the top layer would be flowing with the maximum velocity. So that means with respect to height, the velocity increases. The velocity is increasing with respect to height. Means, let's say there is a shear force. What is shear force? The force acting per unit area, that is along the body, along the surface. So lamina by lamina, they are acting along the surface, not the perpendicular one. So if the force is not acting perpendicularly but acting tangentially, that is called shear. So what is shear stress? Force per unit area. And here we can see that it is acting between the velocity gradients. So du by dy. Okay. And if you remove the constant of proportionality, that's how you get the viscosity. Velocity gradient. So tau is equals to mu v by h, that is the height. If we want the stress force, okay, so force, your drag force in this fluid is equals to, this is F by A, mu v by h, or the F drag would be equal to mu A v by h. So it is the drag between the laminas. The drag force between the laminas is mu A velocity per unit height. Okay. What is dynamic viscosity? So this mu is dynamic viscosity. So it is dynamic viscosity. Okay. What is kinematic viscosity? It is actually mu by rho. So nu is actually mu by rho. Okay, that is kinematic viscosity. Why we are dividing by rho? So that it shouldn't be varying with respect to density. As the density was varying, so the viscosity. So to make it sure that it doesn't vary with velocity, with density, that means to make it specific with the fluid, we must be dividing it by density. Now let's calculate the value of mu. So we can see that from here, this part, mu is equals to FH by A into V, right? A into V. This can be called as L, na? So F area into height, area of cross section, or just put the values. Force is MLT minus 2. This is called pressure. Okay, this is Pascal, and this is H upon H per unit second. So it would be just second. This total will be giving you just second. So the answer would be Pascal second. The unit is Pascal second. So mu has a unit of Pascal second. If you take in centimeters, so only the part that we have is this pressure, in which the dimension is there. Pressure per unit area, force per unit area. In force, there is dimension, length, and in area, there is L square. So if you divide that, so you will be getting it as equals to 10 CGS. This would be equal to 10 poise. 10 poise. What it's called? 10 poise. Now, let's talk about dimension. This is MLT minus 2. That is force. Then height is length. Area is L square. And velocity is L per unit time. So, L per unit time. Let's take the time. Okay. That means ML square T minus 2 or T minus 3 upon, see, L square and then L, that is L cube, or ML minus 1 T minus 3. This is the dimension of mu, viscosity dimension. And they have asked this dimension of viscosity. They have asked the unit of dynamic viscosity, that is Pascal second, or the poise in CGS. Now let's come to this distance viscosity. This is kg per meter cube. So it was ML minus 1 T minus 3, and this is kg per meter cube. So kg is meter cube, that is L minus 3. So it is mm cancels out. This is L power 2 and T minus 3. L power 2 T minus 3. There is a wrong part here. Meter per second to L T minus 1. So this T minus 1 will cancel out, na? So it would be ML square T minus 2 upon L cube into this T would go upward as a plus T. 1 by T, that is this plus T. So that is, or just put it T minus 1. So on the above, there would be just T minus 1. So ML minus 1 T minus 1. ML minus 1 T minus 1. So it is T minus 1. Okay. So it is meter square per second. Meter square per second, or area per second, you can call it. If you convert this meter into centimeter, that is 10 power 4. That is equals to 10 to the power 4 centimeter square per second. And this centimeter square per second in CGS is called Stokes. So 10 power 4 Stokes. So Stoke is a unit of kinematic viscosity. What? Stoke is a unit of kinematic viscosity, while the mu or the Pascal second is the unit of dynamic viscosity. So you must be having the concept of here that is the shear stress is the one that is being developed due to viscosity, and the velocity gradient is there due to the viscosity, and hence the shear can be termed in terms of velocity gradient due to the shear, and the shear is the proportionality constant or the slope, reasoning of this slope in the this and these are proportional, mu acting as a slope. So this slope of curve is nothing but mu. The slope of the stress and velocity gradient curve is nothing but mu. Y is equals to mx. M is the slope. So here mu represents the slope of the curve tau, slope of the curve, shear stress, and the velocity curve, velocity gradient. Okay. Now let's move to the next part. Once we go above it we get like a metal block with a contact area. Contact area is given this much. Rest on a horizontal table. This is the metal block. Contact area is given. Rest on a horizontal block. It is connected by a string passing over a smooth frictionless pulley to a hanging mass of 0.010 kg. So it is 0.010 kg. A thin layer of liquid of this much thickness, that is giving it viscosity above, separates the block from the table surface. When released, the block slides at a steady speed of this. This is the steady speed. Determine the coefficient of viscosity of the liquid. We must know from the previous history that the tau was proposed. Tau is equals to mu into V by H, right? This H is the thickness, means the variation of the viscosity layer by layer. Here we can see the area is given, the force is given, but not the stress. So that means it can be written as force upon area is equals to mu V by H. That means mu is equals to, you should be remembering this, mu is equals to FH by AV, just like we did here. Okay, FH by AV. This is the mu formula. Now, if we come to here, we find out the F acting on it. This side would be acting force would be like this, mg. Let's say it is tension. So T would be equal to mg, na? So T is equals to mg. And here there would be viscous force. Here it would be viscous force in the backward direction because it resists the motion. But the motion is happening in that direction with a constant velocity. So whenever the velocity is constant, that means the net force is zero. Because force means mass into acceleration, means there should be acceleration for a force, net force. So if there is net force, there would be acceleration. Acceleration means velocity would be changing. Acceleration is velocity change per time, means velocity is changing. So whenever there is change in velocity, there would be force. If the velocity is constant, means the net force is zero. Means the force here should be balanced by this. So that means is equals Fv is equals to T. As since del V is equals to 0, means velocity being constant. Okay. So here Fv is equals to T is equals to mg, or Fp is equals to m is 0.01, g is 10, that is 0.1 Newton. Okay. Put those values. 0.1 into the thickness is how much? 0.3 mm. That is 0.3 into 10 to the power minus 3, because 1 meter has thousands millimeters. Upon area, area is given as 0.10, that is 0.1 meter square, that's okay. And velocity is given as 0.085, 0.085. Just you have to solve everything. This cancels out. You can just multiply by 1000 above and below. So it would be 0.3 upon 85. Now again, if you multiply, you will be getting like 30 upon 850. Divide by 5. 5 6 are 30. 5 1s are 5. 5 3s are 15. Okay. So this is the Pascal second by 30, or you can call it like 2 by, no, not do that. So 6 by 13 into 10 to the power minus 1 Pascal second, or 0.6 upon 13, or you can just solve it, whichever answer you find good. See, 13 5 is 65, so it is less than 5, that is less than 5. So it would be 0.04 something, 0.04 something in Pascal second. And if you multiply by 10, you will be getting in poise, or let's say it is 0.6 upon 13 Pascal second is equals to 60 upon 13 poise, as 1 poise, 1 Pascal second is equals to 10 poise. So here it is 4.6 poise. around, you can check the calculation. .61 you can call it. Now let's move to the next one, that is Stokes law. We have already studied that, but Stokes calculated something more amazing. He said that if there is a ball that is dripping around throughout the fluid, so fluid must be viscous fluid so that it can hinder this ball velocity. Means he took an example of glycerine. Why not water? Because water's terminal velocity of a sphere inside water is quite large, so it would require a very large tube. So instead of doing that, he took the example of glycerine and put a steel ball in that and found that the velocity of the ball is quite accelerating with time. Means the gravitational acceleration is acting on it. But after a certain period of time, he found that the velocity remains constant. Means it attained the terminal velocity. Means the drag forces actually balance the weight. So if there is a ball, so what is happening over here? You will find out the ball's weight would be acting downward direction. So ball weight, or that is gravitational force, that is weight. Gravitational force is what? Mass into gravitational acceleration, that is mg. Mass into acceleration is what? Force, that is weight. So weight or gravitational force is same. In the upward direction, we have two things. One is called the buoyant force and the other one is called the drag force. This drag force is given by the Stokes law, that is Fd is equals to 6 pi eta rv or mu rv. 6 pi mu rv. This is the drag force he already gave. For a terminal velocity, these forces must be balanced. Means Fg must be equal to Fb plus Fd. Buoyant force and drag force, if they are equivalent to weight, the velocity would be constant. For Vt, or constant velocity or terminal velocity, that is called terminal velocity. Okay. Now see, this is actually mg. Buoyant force is mass of water that is displaced into g, plus this is 6 pi eta rv or 6 pi mu rv. Okay. What we are trying to do is calculate this v. So 6 pi eta rv, or just do that value. So mass of this object, this is mass of water. Mass of object is rho of object, and because it is a sphere, so it would be 4 by 3 pi r cube. And here mw, mass of this water displaced, is equals to rho of water into volume of water displaced, and volume of water displaced equals to the volume of the sphere. Why? So it would be volume of sphere because it is totally submerged, so it is displacing equivalent water to his volume. So this would be equal to rho of water, or a fluid, you can call it fluid, into volume of that is sphere, 4 by 3 pi r cube plus 6 pi mu rv. Okay. This v that we are about to calculate would be terminal velocity. So 6 pi mu rv would be equal to rho. See, the volume is same for the both. G is missing. See, volume and g is constant. That means only it would be, if we bring this to this side, that would be rho 4 by 3 pi r cube into g into rho o minus rho f. Okay. This v would be, that is terminal velocity, would be equals to 4 by 3 pi r cube g rho o minus rho of fluid upon 6 pi mu r. So here we can see that this is 18. So 4 upon 18 so it is 4, that is 2 by 9. So it would be 2 by 9 mu. And see, pi would cancel out. this would become r square. So 2 r square g rho o minus rho f. Okay, there is no pi and all. So this would be the terminal velocity, 2 r square rho o minus rho f. That is rho of object minus rho of fluid upon 9 times of this mu. So we can get this equation. So the terminal velocity is this. Now if they are asking like these drag forces calculate making the heat in it, and what would be the heat per rate of heat transfer? So rate of heat transfer due to drag force is equals to the power, energy per times power. Power is what? Force into velocity. Drag force is 6 pi eta rv into v. That is, so if they are asking its proportionality with radius, actually this question was asked somehow. So here it is r. For a velocity there is r square and there is again r square. That means it would be r to the power 5. So p proportional to r power 5. This part you should remember. P proportional to r power 5. Means the rate of heat transferred through the drag on the ball is actually proportional to r power 5. And the same way, the terminal velocity is proportional to the r square, means radius square. Okay. So larger the radius, it's that square times would be the terminal velocity. Now, this is the Stokes law, and in Stokes law, you should remember this part. That is important. What is the terminal velocity equation, and you should be knowing the concept over here so that you, whenever required, you can calculate. And next thing is this part, that is the drag force that was derived from Stokes. So Stokes gave us the drag force formula, that is 6 pi mu rv or 6 pi eta rv, whatever you say. Sometimes the radius is written as a, doesn't matter. Whatever you write, that's okay. So you should remember the drag force, you should remember the rest of it. The terminal velocity actually. Now let's come to the next example, that is 9.9. A copper sphere of radius 2 mm is released in a tank containing oil with velocity of this as it falls through the liquid. Determine the coefficient of viscosity. So we know that, like, see how easy this question is. Vt is equals to 2 r square g rho object minus rho of fluid upon 9 mu. So mu would be equal to 2r square g rho o minus rho of fluid upon 9 Vt. Now you put the values, every value, and you will be getting the answer. So it would be like 2 times of radius square, that is 2 into 10 to the power minus 3 square. That is, it would become minus 6, it would become 4. 4 into 10 to the power minus 6. Okay. And the density difference is rho oil. So rho solid minus fluid. Okay. Object minus fluid. So object is 8.9 10 power minus 10 power 3. And the fluid is, oil is 1.5 10 power 3. So that is 8.9 minus 1.5. 8.9 minus 1.5 into 10 to the power 3. Taking 10 power 3 constant. Let's say G to be 10. So let's take it to be 10. Upon the terminal velocity that is given as 6.5 centimeter per second or 6.5 into 10 to the power minus 2 meter per second. Now solve it. You'll be getting here 8. And it is 8.9. 8.9 minus 1.5, that is 4. And this is 7. 7.4 would be the answer. So into 7.4 into 10 to the power minus 2 upon 6.5 into 10 power minus 2. This 10 power minus 2 cancel out. And this would be 8 into 74 upon 65. Nine point something would be the answer. 9 point something would be the answer. So we are calculating the mu, no? So mu would be this much Pascal second. You do the calculation. whichever the option is closest, that would be the answer. 9 point something would be the answer. See, we can take the approximation like 13 5 is 65, 13 6 is 78. So instead of 78, it is 74. But we would be understanding that it should be less than that. So that would be 6, 8, 6, 48 by 5. So 5 9s are 45, means 9 point something should be the answer. So the answer that is closer to this should be our priority. Okay. So instead of doing every tiny bit of calculation, just resolve the 10th power and then make everything closer. If you take everything closer, you will getting the same answer. Like we can do like is 7 and this make to 6. So reducing both. So it would be 56 by 6. So that would be quite a great difference now that we shouldn't do. Anyway, we can come to the close answer. Cohesive and adhesiveness. As I told you guys, if the molecules are attracted to themselves, attraction in same kind, attraction between same kind, and adhesive means attraction with others, whichever is getting in contact with. And I told you guys that most of the time you will find out that viscosity is actually in terms of density. That's why we do kinetic viscosity. So the dynamic viscosity is somehow related with the density. That means whenever we see something that is higher density and has tendency to flow, it avoids the lower density. And whenever we observe a lower density that has tendency of flow, it actually sticks with the higher densities. So let's say there is a water and there is a oil. So whichever is having lower density, that is oil, of course. So oil is having lower density. That means it will try to just get over the water, entire water. Means you can understand such a way, like suppose, just take it as a trick. Suppose lower density means slum people. Lower density means something poorer. And higher density means richer. So what will happen? See, whenever there is a rich person, he would avoid the poor. And whenever there is a rich person, poor would attract towards the rich. Means the lower density people, means poor people, would always attract or try to get over the richer, while the richer would avoid the lower. You get it? Now, let's say if there is a water and oil example, take a water and oil example. So it's a water and you put oil on it. You will find out the whole oil is spreading over the surface of the water. And if you do the reverse thing, like there is oil here and you put water. So water would not be like flowing entire surface. It would make itself separate. There would be distinctive difference in them. And it will make a bubble on that. If the surface is solid, it would just strike from it. Means it won't be sticking with it. Means lower density may be getting attracted with the higher densities. Why? Because higher density means higher intermolecular forces, means those molecules can attach the lower density molecules because they themselves have lower attraction forces. So they would be attracted to the high density. Means the oil would be stick with the solids, while the solids would not, or the higher density would not be sticking with the oils. You get it? Next thing is, whenever we talk about this, we find out anything that is having a lower density with respect to the one that they are in contact with, they will make a surface like this. They try to climb on it. And if it is richer, they try to avoid. And this climbing and this avoiding is actually gives them surface tension. Means if you are trying to avoid everything, you would try to have a minimum area. Means the water inside a air, water droplet inside a air. Air is lower density. Water is of higher density with respect to air. So water is avoiding the air contact. So it would become a droplet, minimum surface area, so that it won't have to contact with the air. So that means it would acquire a minimum surface area, and that's called surface tension. The surface would be tension, hence called surface tension. That is a trick of learning it. Not the concept, it is a trick of learning it, and it would be accurate every time. But in actual, how the surface tension comes? So we know that there are several of the molecules in the water, and these molecules are attracted with each other. So let's say there is a molecule, it is getting attracted from this side and this side. The same goes here, 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 here. They are all attracting with each other, means they are making a rope-like structure, means they are all attached with each other. And the lower molecules, they are pulling them downward. They are pulling them downward also. Means every molecule trying to attract each other so that it is totally tense inside. There is no molecule above. So there is no attraction above, but everything is trying to below. So let's say make a flat surface and try to push every point from the lower point in the downward direction. You will find all a flat surface. You can jump on it. You can dance on it. The same goes here also. The mosquitoes dance on it. They breed on it. And they cause malaria and dengue on it by using that surface area. Now, as their density is higher, that means the attraction forces are higher. That means surface tension is higher. Somehow, if we can lower the density, the surface tension would be lower. That means the density can be lowered by several of the ways, like mixing low density impurities in it. Like what we can do, we can just put oil over it. So oil has lower surface tension, and hence the mosquito will drip down and they will lose their life. And the other thing that we can do is, instead of mixing impurity, we can just raise the temperature. As you raise the temperature, the density slows down, means molecules get away from each other. The molecules having higher energy would tend to separate away because there is a law of thermal expansion. They should expand. And they have got the energy, they have got the currency, they should spend in doing some work. That means they would expand. They would expand means there is lower intermolecular forces, means low interconnection with them, low attraction them. So low attraction in them means lower tension surface area. And if you heat something up to the temperature of the boiling point, at boiling point there is a no free surface. Everything is evaporating. Means during the boil, the surface tension is zero. So at the boiling point, the surface tension becomes zero. The lowest temperature at which the liquid is possible, that was the highest surface tension condition. In water, it is a little bit different. In water, the highest density is at 4 degrees Celsius. Means 4 degrees Celsius, it would show highest tension. Lower than 4, the tension would be lower. Higher than 4 degrees Celsius, the surface tension would be lower. And at the 100 degrees Celsius, the water will boil and the tension would be zero. Surface tension would be zero. Do you got it? This was the concept of surface tension. Now, the next topic comes the drop and bubbles. There is a bubble and there is a drop. So in drop, the free surface is only one. Means if it is a liquid drop, the free surface that is exposed to the atmosphere is one surface. If it is a bubble, the atmosphere is inside and outside. Means inner and outer, there are two surfaces. So surface tension would be twice. But for a bubble, for a droplet, the surface tension would be only one surface available. You get it? So the pressure difference is equals to 4T by R. The derivation is quite longer, so we should be removing this. If for a bubble, if it is bubble, so the pressure difference means del P for a bubble is equals to 4T by R. And for a droplet, the pressure difference is equals to 2T by R. Okay. Now, work done in bubble formation. What is the work done in bubble formation? See, the work done is equals to pressure into volume. So we can do that way, like 4T into that volume and all that. But we can also understand it like work done is equals to force into length, or we can call it as force per unit length into area, and just multiply and divide by length. So it is area, or we can call it, this is called tension, surface tension. So surface tension into area. So surface tension is same for a liquid, a similar nature. So it would be T del A. That means the work done or the energy stored in through a surface tension. So energy stored or the work done. Energy stored or the work done is equals to T del A. If it is a bubble, so it would be 2 times of T del A. If it is droplet, it is just T del A. So the tension, whatever the tension, in bubble there is twice the tension, that is 2T. So whatever the tension is, it is for bubble, it would be 2T del A, means change in area. And change in area would be equals to, that is T del A, means pi R2 square minus R1 square. Like that. So this would be the work done in expanding a area. In expanding a area. And the pressure difference, we have already got that. Pressure difference, we have already got that. Next comes the capillary rise. In capillary rise, we must be understanding that, let's say it's a tube and there is a water in it. It is dipped inside a water. So what will happen? The water will have to like climb up on the surface. Why it should climb up? It will climb up because the density is higher, its density is lower, so it will try to just get on it. The poorer like the richer. Richer don't like poorer. So here it is the tension. We can see that it is the contact. This is called contact angle. It is called contact angle. Okay. So this is the angle of contact. This is the tension. So it would be T cos theta. So upward force is T cos theta. And horizontal force is T sin theta. And the same way T sin theta, they would cancel out. So upward force is T cos theta. And downward force is what? mg. That is the weight. So if it is a tube and the rise is up to here, so we know that the upward force is tension cos theta and downward force is its gravity mg, and mg is rho vg, and the volume below would be what? Volume below would be pi r square h. So the tension is responsible, and the upper force would be equal to tension into the length on which it is attached, that is 2 pi r. So circumference, the tension force is acting on the circumference. It is force per length multiplied by the circumference, that would be force upward direction. This is the force downward direction, that is rho into 2 pi r h. That is 2 pi r h, that is the volume, and then g. Okay. Now equate them both. So 2 pi r T cos theta, and this volume is not 2 pi r h, it is pi r square h. No, pi r square, this is the base area into height, cross section area into height. Yes. Now 2 pi r into T cos theta must be equal to rho pi r square hg. Okay, that is 2 pi r T 2t pi r cos theta upon rho pi r square g is equals to h. See, pi cancels out. This r square cancel out. So it is 2t cos theta upon rho r g, or 4t cos theta upon rho g, and let's say it is diameter. In terms of diameter, the h is this. In terms of radius, the height of rise would be this. And the height of rise is proportional to the tension that is there, and it is inversely proportional to the radius of the, means thicker the tube is, more thicker the tube means lower the capillarity. The capillarity is maximum when the tube is of lower size. Okay, and if the tube is of wider size, that means the capillarity would be lower. So it is inversely proportional to the capillarity, inversely proportional to density, inversely proportional to gravity. Okay, so you should remember those things. Okay, how it behaves with the other things. What are the examples of capillary rise? So capillarity is the example where the example we can point here is the oil is rising in the wick of a lamp. So in a lamp wick, the oil is rising. While we plough the field after the reaping of our harvest. Why? Because there is capillaries in the soil, and they tend to bring all the water below to the surface, and which is dried down. So we break those capillary by just ploughing it, so that the moisture remain in them. Moisture shouldn't be evaporated. Next, blotting paper is a good action of the capillarity. The plants actually take out water from the roots with the action of capillary somehow. And there are several other also. That means the cotton that also sucks up water when it is left out there. So that is also option of a good example of capillary rise. Let's move to the next one. Next one, this is the question. A capillary tube of internal diameter is given. Diameter is given. See, diameter D is given. So the rise H would be equal to 4t cos theta upon rho GD use this example. Or just divide by 2, that is 1 mm r 2t r 2t cos theta rho g r. What into water? Its lower end positions 8 centimeter below. So the height, so what they are doing actually, a tube is there and the lower end, the tube is there. This is, let's say, water level. Lower end is at 8 centimeter below. And what they want a semi-spherical bubble at the bottom. So 8 centimeter below, determine the pressure that must be applied inside the tube to form a hemispherical air bubble at the submerged end. Hemispherical air bubble. And they want the pressure. So what should be the pressure over here is this point. What should be the pressure over here? So we can see that one is one is the pressure due to this fluid. The other one is 80 atmospheric pressure. This is the fluid pressure. And this also has a pressure, and that is called the surface tension pressure. And it is a hemisphere, one side hemisphere. So one side droplet, one free surface droplet has 2T by R as a pressure, but say hemi, so that would be 4T by R. The pressure would be 4T by R. So here it is 4T by R. So this many pressure actually acting over there. Atmospheric, fluid pressure, that is rho GH, and this. So del P is equals to 2T by R, and P in the axis here. You know? It's saying 2T by R. Let's get back to this. Half surface, so it should be half of it. Huh? So whether the droplet is larger or smaller, they are saying that the pressure depends on the pressure, the surface tension, and that remains constant. So let's say here the pressure that you should remain, remember, it's not 4T, it should be 2T by R. Okay, 2T by R. So the pressure on this hemisphere should be 2T by R. Now net excess paper pressure would be atmospheric rho GH, and the del P, that is due to the hemisphere. So this would be a total pressure. Now they are asking us what? Hemisphere over submerged, that is the total pressure, that is rho GH. This is the pressure on the submerged. This del P is equals to 2S by R. This is the value. And now the excess pressure required to form the bubble. The excess pressure that is required to form the bubble is to tackle all these pressures. And to tackle all these pressure, this many pressure must be applied from the inside. Okay, the bubble wants to be getting smaller, not larger. So it's also making the water flow from that. This fluid is also trying to get inside it. This atmospheric pressure also acting here to make it get inside. So that means it should compensate all the three pressures. The excess pressure is this much. Okay. Now comes few more points like what is Archimedes' laws of flotation. Archimedes says that if there is something that is floating on over somewhere, so the buoyant force, if the weight is equals to buoyant force, then it would float. If the weight is being compensated by the buoyant force, means the object that is actually floating, the resultant weight or the experienced weight is actually considered to be zero. Something in flotation means the net weight is zero. It's balanced. Or weight should be balanced by this water that is being pushing it out, that is the buoyant force. Now, the weight of an object is mass of the object into the gravitational acceleration, while the buoyant force is mass of the water into the gravitational acceleration, but mass of the water that is displaced. Okay, so buoyant force is actually equal to the weight of fluid displaced. So weight of buoyant force is actually the weight of the object, weight of the water that is displaced. Now here we can see that G would be cancelled out, of course, and the mass must be equivalent to the mass of the water displaced. That is not true. Why? Because in fluid dynamics, we can't do that. Why? Because the mass is not analogous here. Mass is not relevant here. We should convert into rho, volume of object, into G is equals to rho of water into volume of water displaced into G. This way we should be doing. Now this is the weight, that is the buoyant force that is being applied by the object. Now this object weight is actually the total volume of object, while here weight of volume of the water displaced equals to the submerged volume of object. Submerged volume of object. You get it? Now let's say if something is totally submerged, fully submerged, let's say body fully submerged. So here rho Vg must be equals to rho W Vw into G. And if it is fully submerged, that means the volume of body is entirely under the water. That means the displaced water equal to the volume of the object. So the whole volume becomes equal to the displaced water volume because inside water, it is inside water, right? So we can see that if density is equal, then it would float. Then it would hold, but submergedly. And if the density of the object is greater, it would sink down. So here it is the buoyant force, and here it is the object weight. So weight would be greater if the rest of the things are equal. That means if the density is greater than the water density, it would submerge. If the rest, the volume submerged, if it is submerged in submerged condition, for a submerged condition flotation, the density must be equal. For the submerged condition equation, the densities of the object will equal to the density of the fluid. And if the density is greater of the object, that means it would sink down. It would sink down. If it is lesser, it won't be entering that much in the water. That is, then the volume of the object is greater than volume of water, and it would be rising above. That means density must be far, far lower than the water. Okay. So that means to make something float, the flotation has two conditions. One is this one, other one is this one, and the other one is sank down. So in this condition, rho of object is actually less than rho of water. In this condition, rho of object is equals to rho of water. Here, sank condition, rho of object is greater than rho of. Okay. This was the Archimedes principle, law of flotation. Okay. Next comes the manometer. Manometer, like in the Pascal hydraulics, we just explained. Like if there is a U-tube like this, and there are several of the material inside the U-tube, you have to find the point of similarity. Means let's say from here to here, it's water. Now above here, it's some material filled up to here. And then another material up to here. Let's say another material up to here. And this side also has some material over here. So what will happen, to start with, you have to find the point of singularity. Means here only single material down there. So that means the pressure through this should be equal to pressure through this. Means column A, column B. So pressure in column A must be equal to pressure in column B above this line. Let's say it is H1, it is H2, it is H3, it is H4. So that means H1 rho 1G plus H2 rho 2G should be equal to H3 rho 3 G plus H4 rho 4 G. G on the same side, every side has the G as a common. So G would be cancelled out. That means H1 rho 1 plus H2 rho 2 must be equal to H3 rho 3 plus H4 rho 4. Means the G can be neglected. So while calculating the pressure and solving, we can neglect the G if both the limbs are present, or else we would be considering it. So just understand that if the ends are open, that means this would be equation. Okay. If let's say in a special case, the ends are also closed. Ends are closed, although it should not be in syllabus. Let's say it's a PA. It's column A, it's PA. So here it would be PA plus rho 1 G1 and H1 and so on, SA. And then it is, let's say, open. So here, so whatever the similar boundary you find, just do this plus this. Okay. So it is not in syllabus. Only thing that is in syllabus is this one. Although it is removed this year, but you should be remembering that. Next comes the Magnus effect. What is Magnus effect? Whenever we throw a ball, there is a phenomenon called air swinging. Air swing. So as the ball rotates, one end suffers a higher speed of, like, see, the ball is going this direction and spinning in this way. Okay. So the velocity of air would be like this. Let the V is the velocity, so it would be wind velocity in the same way, right? Now here the ball is actually moving and take this way. So here, see, the relative velocity is 0. Here the velocity becomes almost 0 or lower. While here you can see the ball is moving this way and wind is moving this way, means relative velocity is opposite and hence higher. So this V2, let's say it is V1, above is V1 and here it is V2. So V2 would be greater than V1. And wherever the velocity is higher, V2 would be greater than V1. Wherever the velocity is higher means pressure is lower. So lower pressure, higher pressure means the ball will move this direction. So the ballers do this way swinging, and this swing determines where the ball would go in the air. So air swinging is also based on the Bernoulli principle. Means swinging in the air as a fluid, acting air as a fluid is also application of Bernoulli theorem. It's called Magnus effect. So these are basically the few points that we have already gone through this chapter, but you should remember there are several lots of it. Not everything can be compared, totally discussed here, but we should discuss those. Like Bernoulli, there was question this year. From Bernoulli theorem, there was a question in this year. So from fluid mechanics, there are questions in several of the year. In 2021, there are a lot of questions, like 3 to 4 questions in each shift. Then in 23 there were none, but in this year, that is 25, there were 1-2 questions in each shift. Means this chapter is important. Okay, the last chapter, that is mechanical properties of solids, thermal properties of solid, there were 2 questions in each of the shift. From the mechanical properties of solid, not thermal, the mechanical properties, there were 2 questions in each of the papers. Means these chapters that were considered less important, they are also playing importance and they are confusional. So if you go through this lecture, you will find out there are several of the things that we should be known and we don't know. And I hope that there must have been several of the concepts that must have been cleared in this session. So I hope that you enjoy this lecture and will consider to understand the rest. Like as I promised, by the end of this class, we should be discussing about the course. So the lectures that you are getting today is actually the concept class. So there is a concept class that is in recorded format for each of the lectures, each of the topics. So once there is a concept class that is in recorded format, then there is a live class, this called discussion class. It's a live class. There's a concept class CC that is in recorded format, discussion class that is in live format. We discuss question with you guys. Then there is assignment. Assignment has 20 plus question, means 25, 26, 20, means 20 plus questions are in assignments. Then there is a quiz. It also has 20 plus questions. Then there is a sectional mock, has also 20 plus question. That means while doing these things, like here it is like 50 plus questions in DC, in recorded like around 10 question. So this is 60, 20, 80, 90, 100, 120. So at least 120 while on the first go of the course. And after we do this, there is another quiz 1 and quiz 2 also in some of the chapters. Means then we do revisions, then we again do 50 to 20, 60 questions. There is sectional mocks, then there is a full mock, then there is a live mock, then there is a subject and technical and non-technical mocks. Means you would be able to understand each and every concept crystal clear, and that is also clear through our record of selections. Like through every year for English medium, there is no any platform other than Career Wave that is securing that much results. So that means if you are considering English medium batch, you should be well assured thus that this would be the better platform for you guys. And while doing that, once we do that, there is another batch. Means whenever we complete entire syllabus, then there is, let's say, it's notification time. So once the notification is there, we do everything again, and these foundation batch students have the access to this new batch. So that means you would be doing entire revision once the notification is out. Entire batch would be acting you for as a revision, and then there would be the revision, regular revision for those students who have enrolled in this batch. That would be also accessible. And then afterwards there is a PYQ, then there is a practice session on YouTube. Means at least 1, 2, 3, 4. So including this, there are 5 sessions. Means everything you will be discussing 5 times. That means if you are just willing to put 1 or 2 or 3 hours daily basis, no matter what you do, by the end of these 5 revision or before the exam, I will assure you, I will ensure that you have done everything properly, and you would be much more confident for the examination. There wouldn't be any mistakes if you are just like disciplined enough to at least follow us 75% or more. Not 100%, just 75% or more. If you are sticking with the plan, you would make through it. I won't be suggesting the just test series module only, but like few students just purchase the test series. Test series is for the students that are enrolled, not the students that are not enrolled or haven't studied any time with the Career Wave. Because the test series is as per our course module. Means everything is beneficial if the student is enrolled. If it is not enrolled, he is not enrolled, he will find out like how I am gonna understand what level of question where. Means once you are enrolled in the courses, you know actually what level you are, and on the basis of the level you are in, we actually customize the test series and you go through it. During the notification time, the test series is much more harder. I mean, you find out like in every mock there are 10 to 15 questions that are quite a bit tougher. So that is challenging for the students who haven't enrolled in the Career Wave, but who are enrolled, they find it very easier. So that was all. And one more thing, for English medium only one batch is there, that is Super 50. Okay, Super 50. And once you enroll in that, try to call us and then ask for a coupon if that is available, then enroll in. And once you enroll, make sure that wherever you are enrolling, whichever chapter you are enrolling, right now we are about to discuss like thermal properties of matter. So that means you should be starting from this very chapter, thermo, then KTG, then wave oscillation. And then we will be discussing that 12th part. And once we do that, we would again start from the beginning, and that means the rest of the subject will also be covered. But in the meantime, if you have enough time, you can go through the previous lectures as they are already available. Okay. So once a lecture is done, whether it is live or recorded, it would be available on the platform for later watching. So that was all for today's class, and I hope that you have enjoyed the lecture. I know that this lecture was a little bit of higher length and higher depth, but as we covered the important segment, I hope that I made you very clear in few of the concepts. Okay. So wish you all the best. Take care of yourself and the others. Bye bye. Take care. Good night.